Okay, so far in calculus, we've looked at three big ideas in calculus. The first one is limits, and I hope we are getting close to mastering those. The second big idea that we've been spending a lot of time on here recently is the idea of derivatives. The third big idea, which we haven't spent nearly as much time on, is integrals. Okay, there are two big ideas of integrals, two different types of integrals. The first one is what's called a definite integral, which we have looked at. Remember, that means area under a curve, which we've done by estimating using either counting squares or by putting a series of trapezoids, find the area of each trapezoid, and adding them up. So that's the first type of integral. The second type of integral, which we have not seen yet, is called an indefinite integral. But thankfully, this definition has a name that is very familiar to us, namely an antiderivative. So an indefinite integral is just a fancy way of saying go find the antiderivative. These two words are interchangeable. Okay? But, however, they do involve a new symbol. Okay? An indefinite integral, which is the one I'm going to start with, has this elongated S. Okay? That's the left-hand side of the symbol. The right-hand symbol has the dx. And then whatever you put in between there is what you're going to perform your operation on. Namely, you're going to find its antiderivative. So there will always be an equation in between there. So please note that this elongated s and dx actually disappear when I actually perform the operation. It's not really part of my equation. It's just the symbol that means that. Okay? So some properties of antiderivatives that you need to be aware of is anytime there's a number in front of an equation that you're trying to antiderive, you can imagine the number not being there, go ahead and antiderive the equation, get an answer, and multiply it by that number. Same thing we've shown with derivatives, I've shown this before, is that you can ignore the number out front, find its derivative, and then at the end multiply by the number. So to show you a simple example, let's say I ask you to find the antiderivative of 3 cosine x. So you see how the integral symbol, the equation is in between both the integral symbol and the dx symbol. Well, the antiderivative of that really is the same as 3 times whatever the antiderivative of cosine x dx is. Well, remember, the antiderivative of cosine is sine. So that, oops, sorry, no dx. That is part of the antiderivative symbol. So we just got to remember to go plus c. But remember, we still have that 3 up there, so we got to multiply it by 3. So my answer would be 3 sine x plus c. So if you notice here, 3 wasn't really part of my thought process. I go ahead and found the antiderivative of cosine, and then at the end multiply by 3. Another property you need to be aware of is that when we add two functions together and we're asked to find the antiderivative of that sum, it's actually the antiderivative of each equation separately. So we look at it as two separate problems. So again, as a simple example, let's say I ask you to find the antiderivative of x to the 4th plus secant squared x dx. At first you go, oh my goodness, I haven't learned how to do this, but then you realize these are really just two separate problems. I do them each separately. So the antiderivative of x to the 4th is 1/5 x to the 5th. The antiderivative of secant squared x is tangent of x. And then remember, I have to go the ocean and plus c. Okay, so let's take a look at some examples where we're trying to find the indefinite integral. But remember, that just means find the antiderivative. So the first one here is an anti-chain rule function because I see I have an outside function and an inside function. So there's my outside, there's my inside. So remember, the anti-chain rule says to antiderive the outside, 1/3 to the 3rd power, with respect to the in, so I'm going to leave the in alone. And then I'm going to go back to the inside and find its derivative and divide by that derivative. So in this case, I'm going to divide by 3. So even though I'm thinking to my head dividing by 3, I'm going to write times 1/3 here, and then remember, go to the ocean plus c. Okay, so here's another problem, cosine 8x. Again, I'm going to antiderive what comes between the integral symbol and the dx symbol. So again, this is an anti-chain rule, although the outside function, if you notice, is a trig function. So the antiderivative of cosine is sine with respect to the in. Then I go back to the inside function, and I find its derivative, which in this case is 8. And because it's an anti-chain rule, I know I'm going to divide by 8. So this would be times 1/8, and again, plus c. So here's two more examples. And the antiderivative of secant squared pi x. That sounds like tangent. So remember, the derivative of tangent is secant squared. So the antiderivative of secant squared has to be tangent. But remember, I leave the inside alone. And then to complete the chain rule, I have to divide by the derivative of the inside. In this case, I have to divide by pi. So remember, I don't usually divide by pi. I multiply by its reciprocal, 1 over pi, plus c. And so there's my antiderivative of this function here. Okay, this last problem is a very, very tough antiderivative problem, and one that you really do need to take some time to try to master. So if you look here, you look at this problem, you say, wow, this looks like a product rule problem. If it was a derivatives, you're right, it would be a product rule. But when you antiderive, when you go to, you see something that looks like a product rule, so you say you're going to be an anti-product rule, you need to realize there is no such thing as an anti-product rule. This will always be an anti-chain rule problem. So you have to be very careful because it will look like a product rule from a derivative standpoint, but when you're anti-deriving, it will always be anti-chain. So the first step to this problem is to rewrite it so that cubed is where I'm used to seeing it. So I'm going to go cosine x, the whole thing to the third power, times sine x dx. And now I'm going to do, remember, the anti-chain rule. So I'm going to guess that that 3 is my outside function because it's outside the parentheses. It looks like a reasonable guess to make sure. So I antiderive that. Let's see. To antiderive something to the third power, I add 1 to the exponent, divide by the new exponent. Remember, I have to leave the inside function alone. So it's cosine x on the inside. Oh, okay. So remember, to finish up the anti-chain rule, I have to divide by the derivative. Now, this is where this is different because when I find the derivative, it's not a number. It's actually an equation. Okay, it's the first time we've seen this. Up to this point, it's always divided by a number, although pi is not a normal number, but it's still a number. So you have to divide by an equation, okay? And this is how the anti-chain rule works, because when I divide by this equation, it has to cancel out the rest of the equation, otherwise it can't be done. So in this case, when I divide it by negative sine of x, that sine of x actually cancels out the sine of x, the other part of the integral. But the only thing that doesn't cancel is a negative, so I got to account for it by putting a negative sign out here, and then plus c, and this will be my answer. So once again, this is a problem that's going to take some time here. When you try to do the anti-product rule, there's no such thing. It's an anti-chain rule where the derivative of the inside will actually cancel out the rest of the equation. Practice this and get good at it.